Schema matching is a critical step for integrating diverse biomedical datasets. It is essential to enable analysis and cross-study comparisons, necessary for scientific discovery. Despite efforts to promote the FAIR principles, biomedical data integration remains labor-intensive, error-prone, and costly. To share their data in widely used repositories, such as the Genomic Data Commons, researchers must align or match their data with the underlying schema prescribed by the repository. But doing so is difficult for two main reasons: scale and nuanced semantics. Consider the GDC schema that contains 740 attributes. To harmonize a source dataset with the GDC schema, the researcher must identify for each attribute in the source a matching attribute in the target. Doing this manually is overwhelming. Automated matching tools can simplify this process by pruning spurious matching candidates, but these tools are not foolproof and return many possible candidates that must be curated by an expert. Additionally, nuanced differences between attributes make it difficult even for experts to select the correct match. For example, should the attribute age in the source be mapped to the GDC attributes age at diagnosis, age at onset, or age at index? To address these challenges, we propose bdiviz, an interactive visual analytics system that combines automated matching methods, visualization, and LLM-based validation and explanation. The interface of bdiviz consists of four main components. The interactive heat map summarizes matches across large schemas, allowing users to intuitively explore similarities, filter, and refine matches efficiently, and then accept or reject candidates. Each cell represents a potential match between a source attribute on the vertical axis and a target attribute on the horizontal axis. The cell color represents the confidence on the match. Dark cells correspond to matches with high confidence. To facilitate the exploration of large target schemas, target attributes are clustered in a hierarchy. When the user clicks on a cell, it expands into an embedded node that reveals detailed value distributions for the matching attributes, allowing users to visually compare the attributes. On the left, the control panel allows users to filter the candidate matches, as well as provide quick access to essential operations such as accept, reject, undo, and redo. Whenever a user selects a candidate, they can quickly perform accept, reject, or discard operations by clicking the corresponding shortcut buttons. bdiviz provides filtering tools to facilitate exploration of large spaces of candidate matches. Users can narrow their exploration by selecting specific source attributes to consider, adjusting the Similar Attributes slider to find related source attributes clustered by sentence embeddings, and fine-tuning the Candidate Threshold slider to filter out low-confidence matches. This flexibility allows users to focus on the most relevant candidates, accelerating the curation process. The timeline view displays the user operations as a tree, providing transparency, a clear record of decisions and revisions throughout the schema matching process. Different operations are encoded into different colors uniformly across the whole interface. bdiviz integrates an LEM agent to assist in matching validation. To help inform the user, the agent panel displays explanation cards, offering insights on different factors that contribute to the matching decision, such as semantic and value similarity and external knowledge. The agent provides a decision based on the explanations using chain-of-thought reasoning. As the user accepts and rejects matches, the agent learns from these decisions. Users can readily obtain external knowledge about attributes. The agent panel displays detailed descriptions of target attributes, providing additional context for accepting or rejecting a match. bdiviz is method agnostic and can integrate different schema matching algorithms in an ensemble. The upset plot in the lower panel displays the individual contributions of each method. The lower panel also includes value comparisons that highlight top value matches for the selected source attribute and parallel coordinates to examine relationships between candidate values. Now let's see bdiviz in action for a real use case. Doe et al. Carried out a study on endometrial carcinoma in the context of the Clinical Proteomic Tumor Analysis Consortium, CPTAC. To be included in a pan-cancer analysis that studies multiple cancer types, their data must be mapped to the GDC schema. The source dataset from Doe et al. Consists of 179 attributes. The researchers must identify correspondences between these and the 740 GDC attributes. We use bdiviz to search for additional matches. After the dataset and target schema are specified, bdiviz invokes the schema matching methods to derive candidate correspondences, which are summarized in the interactive heat map. The system automatically identifies and accepts easy matches. Matches with high similarity both in attribute names and values. They are represented as green cells in the heat map. We can verify these matches. For example, phygostage was mapped to phygostage. By checking their values, we can see a clear mapping. IA corresponds to stage IA. IB corresponds to stage IB. BMI mapped to BMI. We can quickly confirm this by comparing their value distributions. The other easy matches can be quickly verified. Now, with the easy matches out of the way, we can focus on the less certain ones. Let's examine the top recommendations suggested by bdiviz. For the attribute histologic grade Phygo, the top recommendations include histologic progression type and histologic progression due to the similarity of attribute names. However, using bdiviz, we observe that neither of these candidates contain similar or equivalent values. The LLM agent confirms that they do not align semantically. Therefore, we reject them. Moving to the third candidate, tumor grade, even though the attribute names differ, the value comparisons reveal clear alignments, such as Phygo grade 1 mapping to G1 and Phygo grade 2 mapping to G2. The agent validation also provides high confidence support for this match, allowing us to confidently accept it. Now let's examine tumor stage pathological. There are two matches suggested for this attribute, phygostage and AJCC pathologic stage, highlighted in blue. But since the target phygostage is already matched to the source phygostage, we can verify AJCC pathologic stage. Let's check the value distributions and their unique value. As we can see, this is a suitable match due to their value correspondences with stage 1, 2, 3, and 4. The attribute age also produces multiple candidates, including age at diagnosis and age at onset. While age at diagnosis has a similar distribution despite being measured in days rather than years, our agent offers the insight that the attributes have similar semantics and names, but their values differ. This can be handled by mapping the values accordingly from days to years. In contrast, the match for age at onset is identified by the agent as a poor match. While the names are similar, the semantics and values differ. We can then confidently accept age at diagnosis as a match. This combination of visual analysis and agent feedback helps users make informed decisions, especially when encountering subtle semantic differences. bdiviz's pattern matching also identifies that WXS normal sample type corresponds to sample type, with the agent explaining the match. The source value, blood normal, aligns with target values like blood-derived normal. By leveraging the similar attribute slider, bdiviz enables users to consolidate source attributes that are related. Here, we successfully map WGS tumor sample type and WXS tumor sample type to sample type. Once the curation process is complete, through the shortcut panel, we can export a mapping specification in JSON or CSV format, which provides transparency and can be used to reproduce the mapping. bdiviz offers a powerful, user-centric approach for tackling challenges in biomedical schema matching. By integrating interactive visualizations, LLM-driven validation, and a user-in-the-loop design, bdiviz enhances accuracy, efficiency, and confidence in curation. Its flexible, scalable approach supports experts in navigating large schemas and resolving nuanced matches, making it a valuable tool for data harmonization in biomedical research and beyond.